In this video, we're going to explore an alternative model of subtraction, the chip abacus model. The chip abacus model starts with an array or table with the place values. So the problem we're going to look at to start off, and we're going to do two problems in this video, is 233 minus 67. So 233 is 2 hundreds, 3 tens, and 3 ones, and we want to take away 67, which is 6 tens and 7 ones. So obviously you cannot take, starting with the ones, cannot take 7 ones from 3, so we need to exchange. We're going to take one of these tens and exchange it for 10 ones, as so. Keeping a record of that, we've taken away 1 10, so we have 2 tens, cross out the 3 tens, and we have 2. We've added those 10 ones to the ones column, so we now have 13 ones. Now you can take 7 from 13, and I'll take these 7 right there. Take those away, and what we're left with is 6 ones, which I mark under the 6, 2 tens, and 2 hundreds. Now, we need to take away 6 tens from the 2 that are remaining. Again, you cannot take 6 tens from 2, so we're going to exchange one of these hundreds for 10 tens, as so. Keeping a record of that, we now have 1 10 remaining, so we cross out the 2, we have 1. We have now 12 tens, so I had those 10 tens to the 2 that were there, so we now have 12. And by the way, I think it's a very good idea to do these tasks in parallel. Whatever you model, the chip abacus or the base 10 block, it's good to write the standard algorithm alongside, sort of in parallel, so that students can see how the actions in the model are reflected in the algorithm that you want them to learn. All right, to finish this off, we need to take 6 tens from the 12 that are there. So here are 6 tens right there, which leaves me with, I'm going to take those away as a takeaway model, leaves me with 6 tens. I'm not taking any hundreds away, so I have 1 100. And that means that in sum, I guess it's in difference rather, 233 minus 67 is 167. The next problem we're going to look at is, to me, the real advantage of the chip abacus model. Okay, with base 10 blocks, you're limited in what you can visualize. You can visualize thousands, are the largest thing you can visualize. And when you have a lot of that, when you have a lot of thousands, you've got a big space you need to fill. Well, I mean, if you had 9,000, that'd be 9 blocks, which takes up a lot of room. The chip abacus model is sort of a nice, efficient way to represent base 10 and base 10 subtraction, but also it allows you to work with bigger numbers, and it allows you to really make transparent the place value in subtraction. So let's work this one problem. We've got 21,343, which I've represented in the chip abacus. We're going to take away 1,672, so we're going to take away 1 1,000, 6 hundreds, 7 tens, and 2 ones. All right, to start off, we can take away, this is kind of nice, we don't need to exchange here, we can take away 2 ones from the 3 that are there. Just take those away, and you're left with 1 1. Okay, now we want to take 7 tens from the 4 that are there. Well, we can't take 7 tens from 4 tens, so we're going to exchange one of these hundreds for 10 tens, as so. All right, so I exchange that. I now have, to cross out the 3, I have 2 hundreds. I have 14 tens. Now, I can take 7 tens from 14. Here are the 7 tens I'll take away. All right, there. That leaves me with 7, which I've already marked up above. Okay. So here's where we are. Now, we need to take away 600s from the 2 that are there. Well, again, I cannot take 600s from 200s, so I'm going to exchange one of these thousands for 10 hundreds. As so. All right, so now I have 0 thousands, and the 10 hundreds that were exchanged, I now have 12 hundreds. Okay, I can take 6 hundreds from these 12. Right there. Take those away, and you're left with 6 hundreds. All right, lastly, our last subtraction, we need to take 1,000 from 0 thousands, but we have no thousands, right? You can't take 1 from 0. So we're going to exchange one of these 10,000s, and you see the pattern, and students will hopefully see the pattern. And that leaves you with this. You've exchanged 1,000 for 10,000s. Now you can, in recording that in the algorithm, you now have 1,000, you have one 10,000 and 10,000s. We can take 1,000 away from that, which is our last takeaway. It leaves us 9. Okay, we are not taking any, we're taking no 10,000s away, so we still have one 10,000. And so via the chip Abacus model, and again recording this via the standard algorithm, 21,343 minus 1,672 is 19,671.